Now let's talk about that subject of global warming and climate change. What it is the fact that the Earth is starting to warm too much. And the cause is too much greenhouse gas. We discussed in the last video that's carbon dioxide, methane, and water vapor. The non-natural sources of those gases, well, carbon dioxide comes from burning fossil fuels like transportation, factories, and producing electricity. Methane comes from rice fields and gassy cows. Now you might argue there's always been rice on the earth. And you might also argue there's always been gassy cows roaming around. But we've never had rice production in such a concentrated area, or cows in such a concentrated area. You just drive around Lancaster County with the windows down. You know exactly what I mean. Water vapor doesn't change. It's not created or destroyed. It's in a cycle, the water cycle, something we've talked about this whole class. So we're just going to focus on carbon dioxide and methane primarily in this discussion. Carbon dioxide accounts for more than half of the greenhouse releases from humans, from burning fossil fuels and cutting down and burning trees. Trees and vegetation absorb carbon dioxide. So if you get rid of it, the carbon dioxide levels are left to increase. And it can stay in our atmosphere anywhere from 50 to thousands of years. Methane comes from raising livestock, from rotting trash in a landfill, and natural gas. It only stays in the atmosphere about 12 years, but it absorbs heat 20 times better than carbon dioxide. The sources of our greenhouse gases from human activities, you can see electricity and transportation top the list, with industry a close third, and agriculture fourth. And we talk a lot about carbon dioxide because it takes up the biggest chunk of the greenhouse gas emissions. In fact, in Mount Washington since 1935, they've been keeping careful track of the average temperature, and they've noticed a statistical increase over time. And that increase goes along with the greenhouse gas carbon dioxide. Now, in the middle of the Pacific Ocean is the island of Hawaii. And on top of Hawaii, there's an observatory that's sniffing the amount of carbon dioxide in the air. I went out on the internet, and you can look this up yourself, and you can see how much carbon dioxide it registered on March 8th, 2017. And it was at 406 parts per million. That's over just the course of a couple hours. You can see it fluctuates pretty quickly. If we look over a month's time, you don't really notice any variability. Back over a season, you see a definite increase there, but it looks like there's a dip coming into October on the left side of the screen. So let's go back and look at a year. And notice, like a wave, it's going up and down. Notice the amount of carbon dioxide drops from the spring going into the fall. While we have land in the southern hemisphere, it's mostly ocean. Most of our land sits up here in the northern hemisphere. And as we enter springtime, the leaves return on the trees. Those leaves absorb carbon dioxide. But when they get to the fall and the leaves fall down, they don't absorb carbon dioxide as effectively. So looking at the graph, now I hope it makes sense that this is cyclical in nature over the course of a season. From the fall into the winter, carbon dioxide levels rise. As we go from spring and the fall, the trees start to absorb that back into their bodies. If we look over the course of 2 years, you can see the waves kind of getting taller and taller. Go back to the 1950s, and you see a definite increase in the amount of carbon dioxide. And it's still cyclical year by year. If we go backwards into the 1700s, you can see that there's a sharp increase in CO2 at the turn of the Industrial Revolution. It starts increasing about 1800, but it really takes a turn in the late 1800s to early 1900s. And going way back in time, carbon dioxide is basically steady, but look at the very end, it's got a very severe uptick. Some people call this the hockey stick graph because that's what it's shaped like. And then there are some people that don't understand how we know how much carbon dioxide was around thousands of years ago. Mauna Loa just started in the 1950s. What about before that time? Well, we can go back even farther than that. And you notice that the carbon dioxide on Earth is cyclical. But nowhere does it really peak above 300 parts per million until you get to the modern era, where we're above 400. How you know it's getting warmer is by a couple different methods. We'll start talking about trees. That's something you learned about in elementary school, that trees have rings, and thicker rings happen in warmer and wetter years. So we don't just look at one tree to determine what year was warm or not. If all the trees seem to have a pattern where they grow in the same year at the same pace, we can say definitively that year must have been warmer. So tree rings are good to correlate our data, but it's not the most accurate way to measure climate. Plus, trees have only been around for 100 or so years, some a little bit older. That's where sea sediments come into play. At the bottom of the ocean, you have things crawling around, and in the ocean, you have things dying. And when they die, they fall to the bottom. When the next thing dies, it falls on top. So gradually over time, you develop layer by layer of dead things. So if you make it to the bottom of the seafloor, where people aren't roaming around digging very often, as you dig a hole, you're actually digging a hole back in time. As we dig a hole back in time, we can look at the seashells that are trapped in that sediment. And we know that the thickness of the seashells is just like the thickness of a tree ring. If there's a lot of carbon in the oceans and it's a warm year, they tend to build thicker shells. Here's an example of a scallop shell with those rings so you can see what I'm talking about. They can also look at the calcium inside the ears of fish. They do the same thing. See the rings there? Those otoliths. They're all trapped in sea sediments. And they can correlate the sea sediments near the top with the tree rings. And they can see that correlation, that warmer years of the tree rings match the warmer years of the shells and the otoliths. To go back farther in time, now you have to look at ice cores. Ice cores are very old in some places where it snows only an inch a year, but it's so cold that it never melts. And some of that ice can be 7,000 feet thick. That's a lot of inches. And just like at the bottom of the seafloor, as you dig down, the ice gets older. You can measure the amount of greenhouse gas trapped in the bubbles inside Greenland's ice. There's an old movie, Jurassic Park, where they get dino DNA out of a trapped mosquito in amber. Some people have no problem believing that that's possible, which it's not. But a gas bubble trapped in the ice, absolutely you can pull the gas out of that, and you can visibly and accurately measure the amount of greenhouse gas in that bubble. That's how we can go back thousands of years. There's evidence CO2 is increasing.
What the scientists here at Rothera have discovered is that this part of Antarctica, the Antarctic Peninsula, is warming more rapidly than anywhere else on the planet. And after years of study, they think the answer to that lies down in the ice underground. I'm climbing down into a crevasse, and it's by getting down into the ice and drilling into it that scientists are able to build up a picture of the greenhouse gases that have been building up in our atmosphere. They find bubbles like this trapped in the ice and analyze the air inside them. This is air from many years ago. And in fact, they now have a record of the atmosphere stretching back 800,000 years. So this cave may to you and I look like a fantastic place of beauty, but for climate scientists, it's a treasure trove of key information.
They don't just look at one ice core either. They look at thousands. And they correlate the ice cores with the seashells that they find in the bottom of the ocean. And with perfect matches, they can start to piece together what the climate was like and what the level of greenhouse gas was. And it gets more complicated. To just go one step further, we'll talk about isotopes of oxygen. Isotopes are atoms that have different size nuclei. So oxygen 18 is actually a little bit heavier than oxygen 16. You can analyze the ratio of 18 to 16 oxygen in the bubbles. In warmer weather, there'll be more O16 evaporated from the oceans because it's lighter than O18. right? The more heat you have, the more shaking you have. So the more energy they have, the more likely they are to fly off into the atmosphere. More heat means more atom shaking, which means more of those atoms jumping out of the water. And you can analyze that ratio trapped in the ice as well. And it correlates with the bubbles, and it correlates with the shells. You can do the same thing for methane, and methane has the same kind of skewed curve over time. In fact, each time methane and carbon dioxide increased for some reason, we had a warming of the planet. And it was cyclical in nature up until about 200 years ago, when we're warming much more than we should be, and we have much higher levels of those gases. And if we go back thousands of years, it's the same drill. Even nitrous oxides increase rapidly at the end with the Industrial Revolution. So one argument is carbon dioxide doesn't account for all the warming that's happening on the Earth. And that doesn't make any sense. You can prove scientifically carbon dioxide results in warming. The planet Mars can be as warm as Earth, though it's 2 times farther away from the sun as us. And many, many, many experiments which you can do at home also prove this. In fact, the television show Mythbusters had a student design an experiment which they did on their show, which can show you how carbon dioxide can warm the air.
The heat's on back at Ice Station Central. The greenhouses are ready, and the Jamie Ice Dolls are chilling out. But can their small-scale greenhouses back at M7 really produce a plausible greenhouse effect? The guys head off to consult an expert at UC Berkeley. And after a little demonstration showing the power of ice...
Oh my God!
It's down to business.
So I've heard a lot about people making models to predict the future of global warming. And with all of the complicated systems on Earth, wouldn't that be a little difficult?
We can do experiments on small scales in the lab. We can make observations on a global scale. But you're right, it is hard to replicate in a 3-foot by 3-foot chamber. It's a challenge. I think it can be done, but it's a challenge to replicate that.
Challenge? That's Mythbusters' second name. And back at M7, it's time to commit the Jamies to a watery grave.
Poor Jamie's looking at you like that.
That ice-cold stare.
Try working with them all the time.
Everything has to be kept identical in this experiment.
That looks good right there. So that's 1,570 foot candles. So let's try to get all the lights so that that amount of light is going into each greenhouse.
Okay.
Accurate thermometers are essential
These thermometers measure 1/10 of a centigrade.
to make sure it all runs to plan. The guys have called in Manish Gupta, a gas monitoring expert from Los Gatos Research. The Earth's CO2 levels stand at around 350 parts per million, and methane a tiny 1,800 parts per billion. But amounts that small are no problem for this gear.
For methane, it's in the part per billion level, and for CO2 in the part per million level.
So now they can up the greenhouse gas levels in minutely accurate increments. And once the gases are in, everyone can chill out and watch ice melt.
Now I want to pause and be very clear about what's going on here. The heat lamps are heating up the black background in the back of this chamber that they've built. The black background, like the ground of the Earth, is heating the air inside. So the lamp is heating the background's heating the air, and the air is heating the ice. That's how it will work in the control box. Now the box with extra greenhouse gas in it is a little bit different. The light is still heating the black background, and the black background is still heating the air inside, but because of the presence of the extra greenhouse gases, those greenhouse gases absorb heat and then re-emit it again, making the air inside warmer. And if greenhouse gases are making the air warmer, the ice will melt faster.
The temperatures have been steady in the control greenhouses, while...
The methane and the CO2 have been a degree higher consistently.
But after 3.5 hours withstanding the heat, the Jamies finally crack.
So we've let the experiment run for 4 hours, and I think from the results that we're getting, we can come to a conclusion. Both the methane and the CO2 greenhouses remained hotter than the control. Throughout the whole experiment, it looks like the gases do increase the temperature inside the greenhouses.
The CO2 greenhouse stayed steady on 24.8 degrees Celsius, the methane on 24.9, and both the controls were consistently a degree cooler.
I think that this is showing that CO2 and methane are major culprits for global warming.
Even in October of 2011, a scientific study that was funded by big oil companies and anti-climate change groups found that they now agree global warming is real. These people have been admitting it for well over 5 years. Another argument is there are natural cycles to make the Earth warmer, and that's absolutely true. The Earth goes through something called Milankovitch cycles, but you have to understand what's happening to really make this case. We know that the Earth rotates just about once every 24 hours, and it goes around the Sun once a year, 365.25 days. But there are other Earth motions that complicate things.
The plane in which Earth travels around the Sun is the ecliptic plane. Earth's spin axis is now tilted 23.5 degrees from perpendicular to this plane. Like an imperfectly spinning top, Earth's spin axis follows a circular trace over time. A full circle takes approximately 26,000 years and is called the precession of the rotational axis. Because of this precession, the North Pole will only point toward the North Star for another few hundred years. The amount of tilt of Earth's spin axis is not a fixed number. The tilt value varies slightly over time. The tilt can decrease or increase, usually over a period of about 41,000 years. In this perspective view of the Sun and Earth, you can see that the red orbit trace is not a circle, it is an ellipse. The yellow ellipse is exaggerated to show how the shape of Earth's orbit trace around the Sun changes over time. This orbit eccentricity changes over about 100,000 years.
So the precession's every 26,000 years, we have an obliquity of 41,000 years, and an eccentricity change of 427,000 years. There are going to be times that the Earth is tilted a little more away from the Sun and is sitting farther away from the Sun in rotation and its obliquity. And that will make it naturally colder. And times we're closer to the Sun, tilted a little more upright, which would make it a little bit warmer. And you can see those cycles in the long-term climate record. You can even see this precession happening in Mexico along a highway, where every year they mark where the actual Tropic of Cancer is. You can see here signs indicating the motion, very slow over a long period of time from 2005 to 2011. So Milankovitch thought that these cycles can account for the large variations in climate over time, like ice ages. The last mini ice age was in the 1200s to 1500s, what we call the Dark Ages. So it makes sense that we're getting warmer. We're coming out of an ice age. The problem is we're getting warmer too fast. Again, we're at 406 parts per million in March of 2017. Another argument is there are other natural sources of greenhouse gas, like volcanoes, and they do erupt and put carbon dioxide in the air. But volcanoes have always erupted on the Earth, sometimes more active than they are today. A dumb and useless fact is only twice have we had ice get to the Gulf of Mexico, 1784 and 1899. And in 1899, the Mississippi was frozen all the way to its mouth, just past New Orleans. The Niagara River also froze that year with Niagara Falls in 1899. Both those years, there was a huge volcanic eruption where there was more CO2 in our atmosphere. But what happened was that blocked the sun. This is the temperature change observed in the United States after Mount Pinatubo erupted in the Philippines. When we went into 1992, we had an abrupt cooling period. If you look at the different volcanoes marked there in different years in the bottom of the graph, and we account for the temperature based just on these natural forcing agents, it should follow the blue line. But what we've observed follows that black line. If you punch into a computer model, natural and human forcing agents, then it matches correctly. Now some people would say, why are we listening to computer models? Well, they don't just fly airplanes to see if they fly for the first time. They have computer models that figure out whether those airplanes can fly or whether those ships can float or whether they can do that surgery on your heart. And we trust them to do that. So it's another example of a computer model making a prediction. A dumb and useless fact along this line is an Icelandic volcano closed down most of Europe's airports for a week in 2010. Stranding millions of passengers, costing $1.7 billion in revenues. You could see the dust cloud from Iceland all the way over to Europe, and that dust cloud was blocking out the sun, cooling that portion of the Earth. Another argument is that the sun activity causes the warming. The sun does go through cycles of many sunspots and fewer sunspots, and higher sun energy and lower solar energy. That comes in 11 to 12-year cycles. But there's no correlation between the temperature and the sun activity. Now for our final dumb fact of the year, maybe not so useless. What's been the warmest year on record? And again, I'm recording this on May 3rd of 2017. Well, as of now, it's 2016. Though if you're watching this in a future year, I'm going to bet it's 2017 or 2018. Because if I look currently at the top 10 warmest years, they've all been since 1998. The top 5 have all been since 2005. All 10 of the warmest years have taken place over the last 20, with each year from 2014, 2015, and 2016 taking over the top spot. In fact, if I look at the local land and ocean temperature for the year 2016, there are very few spots that were near their record coldest temperatures. But all the places in dark red were at their warmest record temperatures. When I first started teaching back in 1997, I used this slide, and I update it every single year. This is a look at the slide I used in 1997. And even back then, I said, hey, 1997 is the warmest year. And with the exception of 1944, 9 out of the top 10 years have been since 1983. The planet is getting warmer, and humans are a reason why. In 1997, the Earth was a half degree above average, and in 2016, it was 3/4 of a degree above average. The Earth has had CO2 fluctuate over time, and it's had higher levels, but it's never had high CO2 and ice caps at the same time. The increased CO2 and the increased temperature is melting our ice caps. 12,000 years ago, we had an ice age. Nowadays, the ice is moving away rather quickly. If we look at satellite readings of the ice from season to season, from 1980 going up to the 2010s, you can see that the extent of the ice is getting smaller and smaller near the North Pole. There are actually now seasons where you can sail and navigate a ship across the northern part of Canada from the Atlantic to the Pacific Ocean. Those ice caps, like ice cubes in a glass of liquid, help keep our planet cooler. And if they go away, the warming will just get faster. This was taken September 10th, 2016, and compared to the maximum extent of the ice at that time of year. You can see a big part is missing over the Bering Strait. Melting sea ice doesn't raise sea level, but melting land ice does. And Greenland's an example where we can see that. This is the extent of Greenland's melting in 2016. And in the summer months, it's been above the average, which is the blue dotted line in the center. The same is happening in Antarctica. This is the amount of mass in Antarctica, and the amount of ice mass is decreasing. That ice is going somewhere. It's draining off the land into the oceans. If we look at this glacier in Austria, this is a photograph taken in 1875, and if we compare it to a more modern picture, the glacier is gone. There's a big lake there now, being held back by a dam. Same is true of the Portage Glacier in Alaska, 1914, to present day. Mount Hood in Oregon in August used to have ice on it still that late in the summer season, but not so much anymore. The Columbia Glacier in Alaska in 2006, and then 2012, just 6 years. We have a time-lapse video of this calving
talks
happening.
about how the retreat is a combination of a glacier dynamic issue and a climate change issue. Tell us about your perception of the climate change part of that equation.
The connection here between climate and the dynamics is that climate, simple melting, isn't what is making the glacier disappear as fast as it is, but climate pushed it into this state. It pushed it into the state where dynamics can take over, start moving ice out into the ocean very rapidly, and once it's in that state, it can't get out of it. The faster it moves, the thinner it gets because of stretching. The really important reason why Columbia is getting small so quickly, it's not because the ice is melting, it's because it's pushing the ice out into the sea and breaking it off as icebergs.
Through the winter of 2008-2009, the glacier flow doesn't keep up at all with the calving rate, and it pulls free of those support points between Caden and Nunatak and rapidly goes back about another half a mile, maybe 3/4 of a mile.
So the ice is not melting per se, but the melting is causing that ice to calve a lot quicker. And that video was back in 2011. If we look at the level of the sea, it's rising an average of 3 millimeters per year. That's 3 coins in height, which is not a lot, but extend that over a long period of time and it can get rather large. It's like a worldwide storm surge. If we continue to have our sea level rise at this rate, you can see what it would do just to downtown Philadelphia, as that ocean water would back up into the Delaware Bay and the Delaware River. Or down at the Jersey Shore, places like Atlantic City become more of an island, and Cape May is underwater. Or down at the Rehoboth Beach and the Delaware beaches, they'll get eroded into the sea. Or down in southern Louisiana, most of that delta will be gone. New Orleans would be an island. Cape Hatteras, you can see this actually happening. This is a picture from Cape Hatteras in 1999, and just a couple years later, you can see how the beach erosion has moved inland. It's why they moved that lighthouse. That lighthouse used to be at the end of that road, but they realized that the sea was eroding away at the beach. So to protect the historic lighthouse, they had to move it inland. If you look at any city on this list, notice each purple line is bigger than the other colored lines before it. And the purple line represents the decade 2010 to 2015. Where the average number of coastal flooding events have increased in all of these cities because the sea level is inching higher.
Recently, I had the opportunity to visit Alaska. I've heard a lot of talk about the effects of climate change in the state. So I asked residents, have they noticed any changes firsthand? Fly to Alaska to see incredible, majestic beauty. You'll also see how the landscape responds to climate change.
The buzzword used to be global warming, but it's not global warming. As you probably know, it's more got to do with global climate change because there are some places on the planet that are cooling down.
Alaska doesn't make the cut on that list. Instead, the state felt a rise in the average temperature over the last 50 years, a rise of about 3 degrees. Long-term fans of the most famous Alaska glaciers know this firsthand.
Case in point would be our Arctic sea ice, and that's been thinning and decreasing in aerial coverage.
While a small amount of Alaska's coastal glaciers actually grow, most glaciers in Alaska shrink.
Most recently, the disheartening part for Juneau residents, because it's our neighborhood glacier, is just how quickly it's disappearing.
As glaciers retreat, some residents can benefit. Kathy Connor from the University of Alaska explains how the ground acts like memory foam. When a massive glacier no longer presses down on the ground, the land gradually responds.
In 100 years, one of the homesteaders got a 9-hole golf course from sea deposits that have lifted up.
Coastal Alaska isn't the only part of the state seeing changes. We're also seeing changes here in western Alaska. The mayor of Nome says that the higher temperatures have affected her isolated community.
You do see when you're driving down the road, some of the power lines in the tundra starting to shift over because the tundra is melting and water starting to pool there.
Blame higher temperatures for melting this usually frozen soil.
In regards to thawing permafrost, when you drive down our roads, you can tell our roads have sunk.
Nome now has to move money in its budget around to deal with the effects from climate change. With this story from Alaska for Eyewitness News, I'm meteorologist Drew Anderson.
So the big question then is it bad? And that's really where our question should lie with our debate. This used to be controversial, and it still kind of is, because it depends who you are. Since 2000, very few people doubt that it's getting warmer. But now we debate how bad it will get, what we should do, and if we should spend any money on it. Looking at the computer models, you can see that they're predicting warmth going on into the next century. And we don't know what exactly will happen. You could have the surface temperature increase a little bit, which is going to evaporate water from the oceans. That water vapor is a greenhouse gas, which will increase the temperature, which will cause more evaporation, and the cycle keeps going. That's a positive feedback loop. But it could also mean if we increase the evaporation of the oceans, we'll have more clouds. The clouds will prevent that heat from hitting the Earth, which is going to cool us down. That's a negative feedback loop. Which one is it? Some common misconceptions, though, are that 95% of the carbon dioxide releases are natural. That is absolutely true. But that's offset by plants absorbing it and the ocean absorbing it. The human release that we have creates the surplus we've experienced since 1832. Another misconception is that water vapor drives more climate change. That is also true. But this can only be controlled by keeping the temperature down. There's no other way we can destroy the amount of water vapor in our atmosphere. It's a water cycle. The other gases then compound water's effect. And climate scientists have an interest in keeping the debate public because it provides more funding. Kind of a cynical response, and that's just false. Under the Obama administration, a Democrat, non-defense spending rose 55%, but of that money, climate research going to science decreased from 56 to 39%. Most of that went to green energy products, which are giving green jobs to the economy. So the moral of the story, global warming is happening. The increase in greenhouse gas cannot be explained by natural causes alone. Some of the cause is due to humans. So until we accept that, then we can start to try to solve the problem if we want to. The argument is now shifted to how bad can it get and can it be stopped? It's an argument of mitigation versus prevention. Mitigation means we fix the problems as they arise, like building seawalls, dealing with famines, moving people away from the shore, increased medical costs. Or prevention, trying to fix it now and try to stop it from happening. There are winners and losers from the impacts of climate change, even within a single region. But globally, the losses are expected to far outweigh the benefits. I had a professor that once said, the Earth's going to be fine. The people might not be fine on it, but the Earth will balance itself out. And one parting thought, Venus is the second planet from the Sun, yet it's the hottest planet in the solar system. It's so hot that lead will melt on its surface. It's 400 degrees warmer than it should be, and it's warmer than Mercury, which is almost in the Sun. This is a runaway greenhouse effect, one where the rate of warming could not be stopped. And another new worry that's been around for now a decade. Our pollution and haze dims the sunlight, which cools the Earth, because the sun heats the ground and the ground heats the Earth. This is called global dimming. In the last 30 years, pollution has dimmed the amount of sunlight, but it still has gotten warmer. Some people are worried it might be too late, because as we clean the air, it might just then get warmer faster. And then you're in a no-win situation. So in the next lesson, we're going to talk about how people have tried to stop the effects of climate change.